Hello, everyone. Welcome to this session of the Asset Performance 4.0 Awards. My name is Wim van Kouwenbergen. I'm Director of BEMAS, and I'm happy to welcome our two next candidates of Siemens Logistics, Mr. Frank Koenig and Mr. Vishal Gupta. Nice to be here, and welcome to the platform.
Yeah, thanks for having us here on your nice conference. So,
yeah, we're very happy that you are here too. So you're going to talk about critical asset monitoring applying machine learning, FFT based on edge and cloud computing. That's a mouthful of a lot of modern terms. So we are in fact very anxious and curious about the solutions that Siemens Logistics is applying. So I'm sure of that you will explain also Siemens Logistics during your presentation.
of course we do, and I think we just give it a start, yeah?
Yeah. So you have the screen already, so you can start presenting, and everyone can ask questions through the Q&A window, and all the questions will be treated after the presentation. So please go ahead.
Okay, so who is Siemens Logistics? So we are a company that has over 50 years experience. We have 3,200 employees worldwide. Our main headquarter is in Constance, Germany. Our second headquarter for airport and cargo and port solution is in Dubai. This is where we are just B2B today. So our portfolio is logistics solutions for baggage, cargo, mail, and parcel. Further, we also have a strong digital approach, digital solutions, and customer service. Further, we have branches in 20 countries. And good, then we go to the next slide. Already starting about talking about maintenance. So logistical systems, they are typically very huge and historically grown. And what we can see is that still corrective maintenance and time-based maintenance are the dominant domains, maintenance domains that customers and us apply. But there's really a strong demand on condition-based and predictive maintenance. So just looking at publications, so far, we did a keyword search on 3 words: condition-based maintenance, predictive maintenance, and condition maintenance. And there were 2,168 papers published. So it's a lot, and what we see in the diagram is it's exponential. So we can clearly see a demand for this technology. So right into our use case, lists. So our bearing parts here are pulleys and timing belts, bearings and shafts, then guide wheels, AC, motor and gearboxes, and also frames, so looseness. So if a management every month is looking at the asset performance, they are looking at the downtime. So we can face in this logistical system 2 types of downtimes. One is related to technical issues, and the other is the daily routine. Yeah, so we can see further details in the next slide. When I say daily routine, this is an example where somebody put a baby buggy with the wheels down on the conveyor. This is unstoppable. Yeah, so that cause all kinds of problems, and there's always a fish hook close by to clear this kind of failures. So what we with our approach are really looking into downtime caused by technical problems. So this is why there is a key. And when it's out of service for several days and that's unplanned, this is our approach. So what we identified on the market, there are 3 different kinds of pillars. The first one is service provider. They offer condition monitoring systems. They have their own systems. they come and bring the system, they go take a asset out of service, install their sensor, capture their data, and yeah, we did this, but our customer said, hey, this is nothing else than time-based maintenance with a condition-based touch. So we get criticized for that. But anyway, these companies are specialized. They are doing a good job, but it's not really what the customer wants these days. Yeah. So there's another strong approach on industrial solutions, and for big industrial systems. Power stations, wind farms, for instance, that make perfectly sense. But for smaller systems, the return of investment is really questioned. Yeah, so we prepare with the capabilities of the IoT a new approach with sensors, self-contained, and we did our trials on these sensors. So what we found out is that there's these sensors. There's one type of sensor where you can set up the measurement to a defined time and for a defined interval. There's another family where you can set up a trigger. Let's say if a device reached a certain amount of vibration, it wakes up and it measures for a certain time. So all these sensors have limited battery life. So what we can see on our hoist, we applied this, keeping in mind that for us, we have still the man in the mix. We are the operator being close to the system, causing all kinds of, we can call it noise. Yeah. So anyway, we applied these two types of sensors. And just to capture some valid data, we have just set it up so that it measured continuously. And yeah, we were able, this is an example from Heathrow, where we had some sensors on the frame. And yeah, we captured the looseness that was already breaking the ice in this, but we also faced some problems. So we clearly saw that if we have good quality data, if we measure frequently and in good quality, the battery life is really short. Yeah, for instance, there's an example where we captured 24/7, and yeah, in 1.5 months the battery was dead. That's not really what we want. We can also have a long battery life, and we measure only once or twice per day. But this is yeah too much compromise. So we additionally, when we look about lifts, we found out there's a big difference if the lift is going against the gravitation or with the gravitation, or if it is loaded or unloaded. So if we have a trigger to measure whenever we want, for instance, when the hoist goes up empty, then we have comparable data. So if you look in the literature, vibration is always described with the spring mass system, and mass is a multiplier. So we have to take this into consideration, and then an external trigger for us is really essential. So we also have a solution, not only listing problems here, we are engineers. So together with a startup sensor system supplier in Belgium, we designed a system, and they were really listening and very cooperative. My PLC that knows the process very well, yeah, I can set a trigger, and within 100 milliseconds, I can set up a measurement. So, and to overcome the battery life restrictions, because I have sensors and field bus module in the field, it's not a problem. We can just put a Y splitter into an existing circuit, and I have 20 volt unrestricted. So we overcome the battery life restrictions, and we overcome the trigger problem. So that's it. Yeah. The first approach for us, we just looked at outliers. So Gauss algorithm so far is not FFT and not machine learning. We were just looking for outliers and we came quite far. But our customers, we're always asking, yeah, but it's okay, but what is the remaining useful life? So I challenged my data scientist, and he said, yeah, he can apply all kinds of algorithms, but he needs historical data. So in the approach, we looked at historical data, and we also made some control tests with faulty bearings and banded shafts so that we get blueprints. So for the most advanced technical part, I give over to my data scientist that's sitting here on the right, ready to go.
Yeah, thanks, Frank. This slide shows how we are going to use data analysis and what is the framework that we have used. So Frank explained all the sensors, IoT sensors that we employed. So these sensors, these IoT-based sensors, are attached all over the asset, and these sensors then communicate with the data server where all the data gets stored ultimately. So raw data gets stored in the data server, and that raw data goes to the edge for cleaning and pre-processing purposes. So the basic idea is to reduce the volume of data by 100:1 ratio. And what we are doing in the edge is we are cleaning the data because there could be man in the mix and the ideal data that sometimes gets captured. And also we are trying to extract the time domain and frequency domain features. Time domains, we generally know RMS values and variance and kurtosis and skewness. These are all statistical parameters that we all know of. Once these features are extracted and the volume of data is reduced from 100:1 ratio, the data is then ultimately sent to the cloud. Cloud, what we have is the trained machine learning. So the idea is to keep a trained machine learning model in the cloud. Whenever it receives the data from the edge, it tries to predict the defect and the remaining useful life. And once it identifies the defect and estimates the remaining useful life, the, the dashboard, the dashboard that we have gets populated. Now this dashboard is available to everyone in the maintenance team. They can see and they can, plan the prediction activities. The maintenance activities in the future. So I'll just go in deeper in all this, the framework, the steps that we have taken. So in the data server, we basically found three types of data. Obviously, first is idle data when the asset is not running; it is standing idle. The second is normal, asset when the asset is operational. There can be defects as well in the captured. So when I say defects, there could be any kind of defect like bearing or roller or any kind of defect or motor or gearbox, anything. And the third category of defects that is actually what we call is man in the mix. So basically, these are all outliers. So the thing is, we have to remove the idle state data and the outliers from the before we do any kind of pre-processing and prediction. So the first one, the removing out the idle data was quite easy using RMS value. If there is not much vibration, just remove that, and that is safe to remove. Removing the outliers, that is man in the mix was quite difficult. Not very difficult, but it was tricky. Thing is, what when we say man in the mix, what it actually means is there is an asset, but there could be maintenance activities going on nearby, or the technician is passing through, or sometimes what we see is someone tries to cross over the conveyor. And if that data gets captured by the sensor, we don't want to use that data for prediction purposes. So we need to remove the man in the mix from the data, and we used this unsupervised learning technique. So this is similar to this is a branch of machine learning, and what we did actually is called multivariate outlier removal. Now, so this technology, I'll just explain what is the first thing, that fast Fourier transformation we are talking about. This is quite an old technology. It's not very new. And in green, the first graph that we are showing, the green chart, that represents vibration captured by the sensor when there is slight wobble in the motor. So slight wobble in the motor is not considered as a defect basically. If there is a lot of wobbling in the motor, then we actually consider it as a defect. So it's not a defect per se, but then we can see the amplitude of vibration varies from 0.5 to minus 0.5. So later on, what we did is we introduced a pulley and timing belt defect in the system. And what we see is the chart in the right side represented in red. Again, with our naked eye, we can't see any difference between green and the red chart. The amplitude are again 0.5 to minus 0.5. But when we apply fast Fourier transformation and we convert this vibration data into the frequency, corresponding frequency, we see a significant change in the pattern, what we call is fingerprint. So you can see 700 hertz, is significantly higher in the second chart, just below the red vibration chart. So this is actually what we what can help us identify the defect. So whenever we see a 700 hertz in the recorded vibration, we can say that this is a pulley and timing belt issue. So that is the technology basically. But the thing is, this is very manual task. We have to identify each and every defect and frequencies and the fingerprints for each and every defect. So this is basically very intensively manual process, and there will be lots and lots of if-else condition. If you go on to code these particular manually defined rules, there will be so many if and else conditions. And the final problem is there could be multivariate interdependencies that can be overlooked by manual process. So the thing is, can we apply machine learning to identify these defects? So yeah, the answer is yes, we can apply. The machine learning will see the patterns, match the patterns, and it will try to identify the defect and say like, yeah, this is the defect, this is the potential defect in the system. But the thing is, we need to train the machine learning model. For that, we need lots and lots of data. But yeah, we had to wait for actually 6 months. Here we are showing. We placed all the sensors on important assets, subcomponent of the components of the assets, and we just waited for 6 months, and we just observed the pattern, actually the trend in the time domain and frequency domain features. For example, we are showing RMS and other frequencies, 100 hertz to 200 and 300 and so on. When we see, when we simply observe the data for 6 months, and whenever we saw any significant change in the pattern recorded, we sent someone to check what was the problem in the system. And the first sudden spike that you can see in the graph, that represents a wheel issue, a roller wheel issue, and the second spike that represents a bearing issue. So those information were then passed on to the maintenance team, which then corrected these faults during their scheduled maintenance. Again, the time-based, we didn't change anything. It was time-based maintenance where it got removed. But the thing is, whenever our team, our maintenance team, or any technician does a maintenance activity, they write it down in an Excel sheet. So we call it a maintenance log. They write in their own language that they have done these things on the particular component, on particular asset. And that information is very important for us to label the data. So we had the vibration data, we extracted all the features, time domain and frequency domains features, and then we had this maintenance log from where we extracted the labels. So the defects that we extracted was using text processing. And once these two data were there, we can apply, we can train the machine learning model into. So these chart actually shows the result of the training and validation process. The first one is related to shallow learning techniques. So first is random forest. The second one is artificial neural network. The third one is supervised support vector machine. So out of these three techniques, we found that random forest was most accurate while validation. And again, machine learning is not, once we have more data, we apply again a different model maybe. So later on, this was in initial phase actually. So later on, we applied deep learning technique that is shown in the fourth graph, and it is actually dense neural network. that we applied, and we were getting approximately similar result as random forest. So yeah, we can actually use the random forest as well as deep neural network, dense neural network for this particular classification purpose. So when we say classification, we had all these labels, like there was bearing issue, there was roller issue, there was draft shaft issue, and maybe there is no defect as well. So we had these labels, and we wanted to predict, whenever these patterns in the data appear, we want to predict it properly, that this relates to bearing, this relates to a wheel, and so on. So in this graph, we are showing like how the machine learning predictions actually classify. So for simple, purpose, for explanation purpose, we are showing random forest regression. It's not classifier, it's a regression where if the yellow dots fall exactly on vertical point 3, so if it exactly falls on this particular line, if you can see the arrow, so it is perfect classification. Similarly, when orange dots, or if all the orange dots falls on category 2, then it is perfect classification. But we see some of the some of misclassification in this graph. Again, if all the dots fall on all the blue dots fall on 0, then it's perfect classification. So we see some misclassification, and that is not big problem. Anyways, we are getting 90% of accuracy, and that is, I guess, sufficient enough. Um, so next thing is remaining useful life prediction. So that was done using nonlinear, or maybe you can use even linear regression technique. Once these data, prediction about the fault and the remaining useful life was available, we populated a dashboard. So in this dashboard, this is available to everyone to see in the Siemens Dubai actually. So in this graph, we are showing on the left top, we are showing conveyor names. So these are all conveyor IDs. So if there is a red, this is something like a traffic light. So if it is a red, then there is a big problem in the asset. If this is yellow, then maybe there could be a problem, but it is not urgent. And green means everything is fine. So this is what we are saying, and then we are showing maybe within these many days we have to, we have to do some kind of maintenance activities. In the bottom left, we are showing the block diagram of the conveyor. We have flange bearing, we have motor, we have the draft shaft assembly, we have idler shaft assembly, we have tension shaft assembly, and all the bearings attached. And this in this one, the green one represents that this particular component is okay, but orange one in this particular example is that where we need to do some kind of maintenance activity, but it is not very urgent case because it's not a red. And then we are showing the data that we had extracted. So again, time domain data and the frequency domain data for anyone to visualize like what is going on, how it is increasing over time, and then the past work orders and the uses of the assets. So once this corona happened in April and everything stopped, so there's no uses then. But then we started using those assets now, which is slightly increasing now uses. So so whenever a technician wants to see what is happening in particular conveyor, he can click on that particular conveyor, and he will be, this pop-up will appear. And this pop-up will contain all the components and all the sub-components. For example, drive contains motor, gearbox, and motor mounting bracket. So again, like a tension unit shaft, drive, non-drive shaft bearing, drive shaft bearing. And out of these, he can see all the sub-components and which particular component may have problems. So the orange one, the tensioning device assembly may have the problem, and we are saying that by probability, with a 42% chance, that 42% chances there is a problem, and then corresponding remaining useful life, it's like 24 days maybe it is there for the maintenance activity. So this is how the dashboard ultimately looks. This is what we have done. Now, I guess Frank will take over from here, and he will explain some managerial things.
Thanks, Risha. So, conclusion and benefits. So, what we found out, and we have 3 projects, one in London, Heathrow, one in Paris, and one in Dubai, where we monitor lifts. So maintenance time spent for inspections. So usually the team is going there. There's weekly, monthly, and yearly inspections. Was significantly reduced, so by 95%. We are just looking at data. We are taking it serious that the remaining useful life for every part, and so far it works really good for us. So also spares consumed was reduced by 37%. The question is why? Normally there is an annual overhaul where the service technician decide if a part gets replaced or not. Now the system is doing it on real conditions, and in the end, the spare part consumption was reduced by 37%. So talking about unplanned maintenance, that was reduced by 80%. That helps a lot. Thank you. So 80%. So we can say that system is working fine. Further summary. Right. The quality data obtained with no dependency on battery life. That was really important that we get data unrestricted, not only samples, so that we can just capture data whenever we want and in a good quantity and quality. And we were able to monitor assets 24/7, and that makes it really accurate. And machine learning models, I think that for more than 70% accuracy, that was really good. So smart allocation of resources according to operational requirements. So it was not required anymore to go there weekly and listen if there's strange noise, yeah, or if because it's very difficult. Some of these hoists are 18 meters built into confined space. It's not so easy to do something with humans and observe this. So, and substitution of sporadic maintenance sites by 24/7 asset monitoring system, that I think we demonstrated in this presentation that this really works good. Responsible use of spare parts, I already mentioned. It's now we do it on real condition and not on judgment from individual. Reduction of unexpected breakdowns. That's really significant, because with this remaining useful life, we reached and taking action before something happens, we reached the zero breakdown target. That's really that was significant. Extension of asset life and increase of available capacity. It is really good if you see upcoming failures very early and you can do something. So this kind of systems are capable to do this. So the maintenance continuous improvement program that we established will continue, and there's customer satisfaction. And we have implemented the predictive maintenance concept in our organization. So thanks for the attention, and welcome to questions.
Thank you, Frank. Thank you, Vishal, for this interesting presentation and for sharing your insights. There have been some questions, so I propose that we dive into this. First of all, okay, regarding the hardware, and let's start with that. There is a question on, okay, if you take a typical installation, how many sensors are required and how many assets are involved? So
on the hoist, we monitor we have two at the frame. We have on every pulley, so we have different lifts. We have S lift and we have hoist. So we have on every bearing, on every pulley, on the frame, on the main motor. That's about it.
Yeah. So it is per unit. How many sensors do you talking about here?
8.
8 sensors, and so you have 8 units. And for instance, at the customer side of Heathrow or so.
No, we have more than hoist in
Yeah.
in airport system. I think in Paris we have 12, in London 5, in Dubai 8.
Yeah, so that's times 8. Is that correct then?
Yeah.
Yeah. Okay. So the number of measures are in fact are quite limited. So one of the questions here was also, okay, in can you talk a little bit about what are the investments involved for setting up such a system?
The development is so developing this system is there's a lot of effort involved. Yeah, so it started in Heathrow, yeah, and we changed the sensor supplier there. Yeah, there were 2 engineers and 1 manager involved. Yeah, not full time. We have many projects, so I have to make a rough guess. What does it take to develop this?
Yeah.
Maybe 3-4 months or to
yeah, development time, because you guys, yeah, okay.
We have a lot of projects, and this is a guess now, yeah.
Yeah, okay, no, okay. And so from the side, from the hardware, what were there the costs?
This IoT sensors compared to other systems, because you remember the 3 pillars, yeah. The base station about 250 euros, and the sensor close to 200. Yeah.
Okay.
Plus installation material. Yeah. Maybe for a hoist, installation and labor, maybe 5,000-6,000 euros.
Okay.
The hardware cost compared to the development cost
This was.
So it's not a big part. Yeah. So,
yeah. Okay.
Yeah.
So.
And just going through all the hoops. This is the challenge. Yeah.
Yeah. Okay. And so, how many equipments are currently running the system?
You mean?
Well, yeah, maybe. Yeah. So you have 3 locations. Is it correct?
Yeah.
And then on those 3 combined, how many conveyor belt systems?
This is they're all airports. They're
Yeah.
all major hub airports.
Yeah.
And yeah, we are not monitoring only hoists. We are monitoring reclaim carousels. We are monitoring straight conveyors, selected straight conveyors. We have a customer approach. We always ask them, hey, what line do you never want to lose? What makes you the most headache? Yeah, because this airport, yeah, they have in Dubai, they have 40,000 assets.
Yeah.
Nobody will make an investment and put a sensor on every asset. So there is a model where we involve our customer and say, what is the most critical asset?
Yes. Okay.
And we do this approach. And because this hoist, yeah, the problem of baggage handling system, they are built into the building is not designed for the technical system. We are always custom built the system into an existing building. So there is also sometimes a compromise. This is why you have to use the hoist to go from level 5 down to level 0. Yeah. So the hoist is a critical asset. If you lose the hoist, yeah, and there is no redundancy because of the building. If you lose the hoist, they are dead. So this is why hoist is always
Okay.
the list of critical assets.
Yeah, okay. And so you have invested there these months of engineering into the solution, but in how far is the solution scalable? So can you apply it on other types of equipment, or can you apply it to the same type of equipment on the different locations and different circumstances? Is it easy to scale, or is it more quite difficult to scale?
Now it is with this sensor technology, especially this external trigger, the technical world is open. Yeah, I make an example. I got a request. Can you monitor power rails? Yes, we can. Yeah, and there you need a trigger because this yeah, let's say on a cargo vehicle, the power rail is several hundred meters long. It doesn't help my customer that I say, hey, your power rail is full. So they really want to know where. Yeah, and 100 meters. If you have a trigger, you know the PLC know I'm now at the home position, and then now I'm driving forward. So by a simple calculation, SVT, you can calculate where the problem is. So the trigger is very important. So we are using this for monitoring conductor rails. We also use the trigger for, we have applications where we have to lift up, it's like a train, yeah, a cargo train, so that the wheel is spinning free, so that we don't capture all the noise. So the trigger, the external trigger for an IoT sensor is really something that broke the ice. Yeah.
Yep.
And overcoming the battery restrictions. I try to explain in my part of the presentation. These battery powered sensors, they really have the, let's say for a compressor, it is good. The compressor starts, the sensor wakes up. If you measure for, let's say, 10 minutes, job done. Yeah. Or on the pump that is running 24/7. It is good. You measure at 12 o'clock, you measure for 10 minutes, you have all the data you need. But in logistical systems, the difference is, I always make a joke. Our systems, our assets are standing in idle until an item is coming and this needs to be transported. Yeah. So if you just do it with a timer, it's something like a lottery. You don't capture
Yeah.
it.
Yeah.
If you do it just with this wake up principle, you're not capturing everything because looseness. I had one incident in Heathrow where the frame was getting loose. You don't capture it with this. So the combination overcoming the battery restriction, and there's always sensors in the field where you this sensor has only a power consumption of 4 to 10 milliamps, so you can easily put a wide splitter between a photo eye and the field bus module, and yeah, and it's forever. So you don't have to make a compromise. That was important for us. So external trigger, overcome the battery power life restrictions, and then my data scientist is happy because he gets enough data in a good quantity, in a good quality, and he can apply all this new and good machine learning models and FFTs. And by the way, this predictive element, yeah, every customer asks me, hey, what is the remaining useful life? And without having data in a good quantity and good quality available, you can't predict anything. So that's the advantage.
Yeah. Well, there is a question on this remaining life, useful life. I think that's maybe more a question for Vishal here. So, in fact, there is a question on how the remaining days or the days until maintenance are calculated. There is a sheet in your. Maybe you can revert back to that sheet. There is a sheet where you have this kind of well. Yes, here it is. So these green flags are days until maintenance. That's correct?
So simply, it's like we know the maximum acceptable value of these, features. Like what is the maximum acceptable level of RMS value of the vibration,
Uh-huh.
and we know what is the present value of the RMS value, and we
Yeah.
know the maximum value. And if we plot a regression model over this, we can extrapolate this model over the time and see, okay, so this RMS value will reach to this maximum acceptable value in these many days. So that is particularly what is called
Yeah.
nonlinear supply. So there are so many models. We have used nonlinear model here, nonlinear regression.
Yeah.
Uh,
Okay. And so in the same graph, we also see this percentage of probability. Can you also explain a little bit what does that mean? Is that the
yeah,
probability that it will get to 231 days, or is that the probability that it will fail the bearing? What is it?
no, it's like what we are doing here is the sensors that we have installed is capturing data every half an hour.
Mm-hmm.
So many data, and now if we see one reading, so 1 second reading or 2 second reading, it will be classified into some category. Like when we classify it into, it will fall into this particular defect category. But then again, after half an hour, maybe it will not particularly fall into any category. Maybe it says there is no fault. So means when we input all these, so let's say we had 100 readings for a day, or maybe for a week. The model will try to say, okay, how many times this particular kind of defects appears in these 100 readings. So that's what it means.
Okay. Yeah. So it's an indication of how many times this problem has been confirmed, in fact.
Yeah, yeah.
Okay. Oh, that's an interesting approach. Huh? So um, a question. One of the things that struck me also is that you're doing the machine learning models on the RMS, or are you doing it on the complete spectrum of the Fourier transformation?
Okay, I'll explain that one.
Yeah.
So here we are showing the time domain features and the frequency domain features that we extracted. So when I say the volume of data was reduced from by 100 is to 1, so actually each and every reading that we captured had maybe 40,000 readings. And
Yeah.
when we extracted these features, it reduced to 40 readings, means 40 data points. That could be RMS, kurtosis, variance, and all these statistical parameters and the frequency domain parameters. So total in 40, from 4,002, we got 40. Now these 40 data points were then feed into the machine learning model, not just the RMS value, but
Yeah.
all these
Okay.
values.
So you have a lot of characteristics on the vibration pattern, and
Yeah.
you're using all these characteristics. Okay, nice. And so you had also a very nice picture in the beginning of your presentation where you have this wheelchair blocking something. And so the question there is, yeah, I think it was almost in the beginning of the presentation, wasn't it? Yeah, this one. Yeah, very nice. So the question is, how can you differentiate between what seems to be an operational problem and a technical problem?
We have a noise. Yeah, okay. We go. There is, we can see this. 1 second. Where is it? Do you see my cursor?
Yes, we do.
This is a classical thing because you see this blue, this is cluster 2. That means the machine is in idle, but there is one outlier during the time of idle. This is yeah, a typical man in the mix.
Okay, man in the mix. So then there is, yeah, the human error, even the human literally here. Huh? Okay. So and does that raise an alarm?
Nope.
No, it doesn't. So it's ignored as it should be.
We want to filter this out.
Yeah. Okay. For the okay. Good. And so it is filtered out.
So there is a Maximo does this red trigger is whenever the conveyor is stuck, the engineers on site will know about that.
Yeah.
So that is a solution already present in the system.
Yeah. It could be used somehow to raise an alarm for the operators in the neighborhood. So look, attention, there is something wrong here. Is that possible, or do you have too many false outliers? So how can you differentiate between the false outliers and the right outliers, or the relevant outliers?
You label this.
Yeah. So thing is, when we talk about stuck wheelchair in the system, that will actually stop the conveyor. The conveyor will trip on that particular case, and there will be blockage in the system. Anyways, the sensor will be recording idle data
Yeah.
because the conveyor is not running. But at the same time, the control room will know that the line is stuck, and they will send someone because
Yeah.
they continuously observe these operational faults.
Yeah. Okay.
I
So
mean, it really took a while to label this, and we used historical data for that.
yeah.
And yeah, that's challenging. And this is why we came also up that we need an external trigger. Yeah.
Yeah.
So if you just measure and you have the data and you're in your ivory tower and you don't know what's going on, it is very difficult to put a label on the special fingerprint. Yeah, this is, but the cluster here is really nice. You see the blue one is, this is really classical idle time. Yeah, and yeah, this the nice little X there is the man in the mix. Yeah.
Yeah. Okay. Interesting. Interesting. So another thing is, of course, when you're the system is a living thing. You do have technical interventions. So the question is, for instance, if you have a lubrication round done, do you notice that in the figures? And can you say, look, there has been a good quality lubrication, or lubrication is still due, or it has not been done right? So do you see that in the data?
Yeah, the very interesting thing, and we overlaid the work orders. Yeah, you see this is coming from the maintenance management system.
Yes.
So you if you go one further, oops, no, oops, where is it? Oh, okay, we go back.
No, actually, the answer to your question is yes. We see a significant reduction in RMS and these features. When there is good lubrication, or even if there is some kind of maintenance activities, we'll see the data to improve.
Yeah, and all the way around, does the system also alert for, yeah, it's necessary to lubricate now? Because this is, of course, something, a condition that is growing very steadily and very slowly, isn't it?
Yeah, the bearing has a what is it called, grease nipple?
So in this example, we are showing bearing issue, right? But before that, the maintenance team, we alerted actually them that there is a problem, and they greased it. But after greasing, on later stage, we found that there is a problem in the bearing. So yeah, the
Yeah.
grease does get captured, and
Yeah. Okay, so you can determine. So it's quite interesting to play around. If you go maybe one slide further, I think there is another question there. Yes, here. So can you explain a little bit what is this training score and this cross validation score? What is the difference and where does it come from?
okay, so the idea is when we, apply supervised machine learning,
Yeah.
we need to have labels for each and every data that we have captured. So I talked about 40 data points that we had. for each and every reading that we captured. Those data had to be labeled for particular kind of defects like bearing roller or any like these kind of, there could be any number of defects. But then once we have these labels and the data with us, we try to train the model, the machine learning model, to predict. And during that time, we divide the data into two categories. Like one is used for training purpose and one is used for validation purpose. And so when we train the model, we want to see if it is learning properly when it is given a new set of data. So let's say we had this much of data where we had labeled, and we separate out some portion of the data for later on to see if it is being, because
Yeah.
when we are using data that is the model is already exposed to, maybe it will predict more accurately. But when the data is entirely new, maybe it will not be able to predict properly. So that's what is validation and cross-validation and training.
Yeah. Okay, so I think we have time for a final question. And for the final question, I would like to go back a little bit to the final slide with the impact, the business impact, Frank, on yeah. So that's a little bit further on. Yeah, there you had it. Maybe just one slide back. Yeah. Okay. So I would just like to go a little bit deeper in each of these ones to try to understand. Okay, first of all, what is the cause for this? So you say, okay, look, the routine maintenance inspections have gone down by 95%. Does that mean that you almost don't do any inspection anymore? So that's then visual inspection, or what are other type of inspections?
Before we had stuff in the system, and they were just on a daily basis checking this. Yeah, we had we have a maintenance program. Yeah, so weekly
Yeah.
inspection is a little bit more than daily inspection. Yeah.
Yeah.
And monthly inspection is also measuring something. And
Yeah.
we have also a yearly overhaul. That was the time-based maintenance program. That was all used to. We are just looking at data, and we just looking at if the system is telling us there is for instance, you saw this guide roller. Yeah, there is a defect. Then and the defect means there is not yet downtime. Yeah, it can maybe still operate with this defect for months, but we can choose on these airports. You have class 1 premier days. Okay, maybe not under Corona anymore. Yeah, but we had premier days where there were so many passengers where we not even were come close. Yeah, we would also operate it with a faulty bearing until it is really falling apart. Yeah, but there's days where it's not so many action. Yeah, so and then you can do. You can use an alternative route, and you can really do your maintenance plans on a day where there's not so many action.
Yeah. Okay. So I can imagine that by reducing these inspections a lot, it had a financial impact. So can you talk a little bit here? Maybe you have less staff now, or what was the impact of this?
I can tell you, when you deal with Heathrow or Charles de Gaulle or Dubai Airport, they will not tell you that what the success indicator for us is. First, you have 2 prototypes, and when the customer is happy and they ordered to install this for the rest of all hoists, that's an indicator for us that this is really good. Yeah.
Yeah. Okay. So you don't have a look. You don't know what is the impact on for the business case there, but you do understand that the customer was very happy with this. So then you see here the spares consumption minus 37%. So that doesn't make you happy because you supply these spares.
Yeah, it depends. In Dubai, we are the company that's doing operational maintenance, and we get a nice benefit, a nice bonus if we our KPIs.
Yeah.
And these KPIs, for instance, there is one KPI is called the in-system time. Yeah, this is easy to measure because these systems, they are, can you imagine this 200 kilometers of conveyor?
Yeah.
You know, the time when the bag was checked in and when the
Yeah.
bag reached the final
Yeah.
loading point to aircraft.
Yeah.
This time is known. So
Mm-hmm.
the impact on this time, if you have a lot of failure in the system, the in-system time is very high. So
Yeah.
1 KPI is the in-system time, and you not for a day, but you have it for an
For
entire
you,
year.
yes. Mm-hmm.
If the system has a lot of failure,
Yeah,
your
they have a
in-system
low. Yeah.
is very high. So
Okay. Yeah.
we get a bonus if the in-system time
Okay,
is
it's got higher, and so this helps you to get this bonus.
and we can also pay penalties if the in-system time reached a certain level because then we're doing a lousy job.
Yeah. Okay.
So, but
yeah. Perfect. Okay, I'm sorry for interrupting you, but because we have to close down, we are at the end of our time available because on the hour we are starting the presentation of the next candidate. So I want to stop this presentation and by thanking you both for explaining your insights. Was really useful and really interesting for us. So please follow also the other presentations. So anyhow, I would say, look, people that have watched this presentation can rate it and help to decide who will become the winner of the Asset Performance 4.0 award this year. So here you have a QR code that you can use with a mobile phone, or you just can go to bit.ly/APA 2020. So this will help you rating the presentations and rating and deciding who will win the award. Thank you very much, everyone.